Today's experiments are all about hyperbolic geometry. So Euclidean geometry is what we are spending most of our time on in this class. Euclidean is the geometry of Euclid. It's our nice flat plane that's modeled well by a flat piece of paper. You spent a little time experimenting with spheres and what spherical geometry would be like. There's a third kind of geometry that's been pretty important for understanding how axioms and theorems work and how geometry really works, and that is hyperbolic geometry, which is sometimes called Lobachevskian geometry. So Nikolai Lobachevsky was one of several discoverers of hyperbolic geometry. He was the one who was perhaps the most persistent in convincing people that this was a real, consistent geometric structure, that you really could have something that fits these axioms. So we'll talk more about those axioms when we get to a very famous axiom, which is the parallel postulate, later this semester. But our first two axioms, the one about distances and the one about ordering points on a line, and our definitions of segment and line, work just as well in a hyperbolic geometry model as they do in a Euclidean geometry model. So this picture over on the left, figure 2, is a picture of something called a pseudosphere. And that was maybe the first picture model of what a hyperbolic plane is like. And you'll see in my other videos me showing you how it works on a crocheted model of what the hyperbolic plane looks like. Now the problem with my crocheted model and the problem with this pseudosphere, think of it as being like, the horn on a trumpet, the end on a trumpet. The problem with this is it's hard to draw. And so a thing that several people have done with hyperbolic geometry is they've figured out how to make a flat map of the hyperbolic plane. So they figured out how to make a flat map of it. So when you think about maps, probably one of the images of a map that you have in your brain is this sort of map of the Earth. This is the Mercator projection of a map of the Earth, and it has some advantages and it has some disadvantages. So turns out it's useful for navigation because you can do things nicely with angles on this map, and the things that you do with angles gives you the same angles you would get if you measured them like we were measuring angles on a sphere. So angles are preserved by this map projection. Distances are not. So Antarctica is not nearly as big as it looks on this map. If I wanted to, if you remember when we looked at the sphere from Google Earth and we were looking at how you would fly if you wanted to fly from somewhere up here in the northeast United States or Canada, and you were flying over to somewhere in northern Europe, you had kind of this way that took you up and over, and that was a shortest path. And this path where I go straight across along the latitude, that's not a straightest path. And so distances are not preserved on this map. So if you wanted to tell somebody, if you pick a point up here in I think that's New Brunswick, Canada, and you pick a point over here in Sweden, and you want to figure out how far it is then you'd have to make some sort of a function that told you, oh, all right, so first you start off with this information about the points on the map. And then I need to multiply by something or divide by something depending on how far north or south those points are, so that I can take a distance on the map and turn it into a distance on the sphere. So the map we're going to look at today is a map of the hyperbolic plane, and it, similar to this Mercator projection, is going to preserve angles. So if you draw an angle in this map of the hyperbolic plane, that's going to be, and you measure it in the picture with your protractor, that's going to be the angle that really would be there if you got out my crochet hyperbolic plane and you measured it on there. So angles are going to be preserved. But what's not going to be preserved is distances. So up here, you know, it looks like these points at the North Pole are really far apart. They're really close together. And the opposite happens in a map of the hyperbolic plane. So let me pull up a map of the hyperbolic plane. I think I want that one. This is a particular famous map of the hyperbolic plane. It is called the Poincare Disk. Okay, so I'm going to add this in here. What we are looking at is the Poincare Disk. And that E should have a little accent over it, but I don't remember the keyboard thingy to give you the right accent over the E. So this particular map of the hyperbolic plane is one that was invented by Henri Poincare. And what it is it is a map of the hyperbolic plane, which, as you remember, it looks little, but in fact you're only seeing a little bit of it, and it goes off infinitely far in every direction. And so this is something that takes an infinite plane and it projects it down into a map that fits inside of a disk. So the points of the hyperbolic plane, as mapped out in this Poincare disk, if you get closer and closer to the edge of the Poincare disk, you are going further and further and further out. And so the points on the edge of this disk aren't technically in the hyperbolic plane. That's like infinitely far out there. So here we have it. We have a Poincare disk. So I need to tell you a few things about what you're looking at here. So I'm going to pull up a different map of the Poincare disk. So one of the ideas that Poincare was building off of is there's a notion called inversion in a circle. And a circle inversion is kind of like a reflection, only instead of reflecting across a line, you're reflecting in and out of a circle. And so if I pick this, the inside of this circle with radius 1, that's going to be my map of the hyperbolic plane. So that's where my hyperbolic plane map lives, that's the Poincare disk. And I'm going to draw another, I'm going to draw one of the lines that are hyperbolic shortest paths. And so it turns out that there's a way to do this that involves circle inversion. And so I'm just going to do one example of how you would make a hyperbolic shortest path in this Poincare disk. And you start off with a point here that is inside the disk. And so my hyperbolic straight path is going to go through that point. And it's actually going to be perpendicular to the line from the center of the circle out to that point. And what I need from that is I need the distance from A to C. So let's see. Distance A to C. There we go. There's my distance. Now, if I take C and I reflect it outside of that circle, then the outside reflection point of C is going to be 1 over this length away from the origin. Okay, so my reflected point is going to lie on this ray. Where's my ray tool? There's my ray tool. It's going to lie on that ray, and its distance from the center is going to be 1 over that length. What's a good way of doing that? I don't have a good way of doing that. I'm just going to make a circle that has that radius. So first I'm going to calculate that length, that 1 over. Okay, so that's how far away from the center it's going to be. I'm going to go ahead and make me a circle with that radius. I'm just going to do it this way. There we go. So the reflection of C is right there, that point right there. Okay, so these are going to be 2 points on the shortest path line in the Poincare disk map of the hyperbolic plane. So I'm going to have to find the center of that circle. It's going to be a midpoint right here. Where is my midpoint tool? Midpoint tool. Okay, there's my midpoint. I'm going to make a circle that has C and D on it and has the midpoint there. All right. Okay, so this here, so a thing that happens because of this reflection property, and this reflection property also preserves angles even though it changes distances. A thing that happens is that this circle and this circle meet at a 90-degree angle. And that is the property. It's this reflection property, which is the same as the 90-degree angle property. That means that if I put 2 points on the arc that is just this part of the circle, right? Because only the stuff inside this disk is part of my map of the hyperbolic plane. But things on this arc are on a hyperbolic straight line.